evening, and welcome to those of you in the room to the Royal Society of Edinburgh, and welcome to those of you joining us online on YouTube. We're thrilled to have you join us here this evening as part of the Curious Festival of Knowledge. My name is Laura Stephen, and I am the Director of Finance and Corporate Services at the RSC. I joined the RSC during April this year, so this is my first Curious Festival, and I hope you're enjoying the programme of events as much as I am. As always, a little bit of housekeeping before we get started. Please note that the RSC's fire and evacuation procedure is to assemble outside the dome, and you leave the building the way you came in. So through that door and then out to the street and to your right. The fire exit routes are currently on the slide. Yes, they are. Thank you, Rab. But please follow the Curious staff instructions in the case of an evacuation. We're not expecting an alarm, but the Curious staff will be on hand to help guide you if the fire alarm does go off. And can I ask the Curious staff at the back of the room to give us a wave? Easily identified in the purple tops at the back there. So now, back to why we're all here, climate change. When you come to an event like this, you want to make sure you're listening to someone who knows what they're talking about. And I can assure you, you are in good hands tonight. Dr James Rae is a climate scientist and geochemist in the School of Earth and Environmental Sciences. A geologist by training, much of his work investigates Earth's climate history using the chemical footprints of past climates encoded in fossils, minerals and ice, measured in his world-leading laboratory at the University of St Andrews. Dr Rae's research has been recognised with honours, including the Outstanding Young Scientist Award from the European Geosciences Union, major funding awards, and the election to the Young Academy of Scotland. You're all in for a fantastic evening, after which you'll have a chance to ask questions of our speaker. We won't be taking questions during the talk, so please keep any questions ready for the Q&A afterwards. So without further ado, please welcome to the stage Dr James Rae.
Okay, so hello everyone. It's a real pleasure to be here with you this evening to speak about the 3 S's of climate change. First up, that the science of climate change is actually surprisingly simple. Secondly, the impacts of climate change are really serious. And then finally, most importantly, that this problem is solvable. So let's dig in. When the magnificent Edinburgh Castle, and I realise it's maybe not the most magnificent clip art, but when this magnificent castle was founded in our amazing city in the year 1103, carbon dioxide in the atmosphere was at a level of about 280 parts per million in the atmosphere. 280 was the level of this climate warming gas throughout almost all of human history as we think of it. This was the amount of CO2 in the atmosphere when agriculture was started, when the pyramids were built, and the Great Wall of China. But it was also the level of CO2 when a Scotsman, James Watt, invented his steam engine, a device that turned the most carbon-rich substances on our planet, coal, oil and gas, directly into atmospheric CO2. CO2 is today elevated to a level of 425 parts per million. And if you think that 425 parts per million, so how many molecules of the air is made up of CO2, if you think that, 400 within a million doesn't sound like very much. For context, that's the equivalent concentration to 2,000 adults peeing into an Olympic-sized swimming pool. That's the equivalent urine concentration, after which you might feel slightly iffy about going for a swim. So small amounts of important substances can have an important effect. If we want to understand this level of CO2 and what it does to our planet, you can see from this graph that we're not going to be able to find that answer from human history. So today I want to take us on a geological journey deeper into our planet's history and try and work out what we can learn about present and future climates from the climates of the distant past. So to do this, our first tool, our geological climate time machine, if you like, is this amazing tube of ice from Antarctica. It's laid down in layers. These layers record years. And within this ice, if we take a little slice through it and look at that under a microscope, that's what you can see in this image here. And you can see these tiny bubbles of air trapped between the ice crystals. These air bubbles are literally a fossil record of our atmosphere. And so we can get an amazing record of the carbon content of the atmosphere by cracking open these bubbles and seeing how much CO2 comes out. And that's what I'm going to show you on this graph here. The human history part of time is now compressed into this small segment here. And we're going to go back in time 800,000 years. Again, with carbon dioxide levels going up and down. What you can see when we do that is that there has been this regular oscillation in carbon dioxide levels over the last 800,000 years. And these have been associated with really massive changes in climate. The most recent one of these was here, the last ice age. This is a time with a kilometre of ice on top of where we're currently sitting. In fact, so much water was taken out of the ocean and stored on land in massive ice sheets that sea level globally was 120 metres lower than it is today. Then at the end of the last ice age, the CO2 rises, the ice melts back, we have 120 metres of sea level rise, and this ushers in this period of relatively stable climate in which all human civilization, as we think of it, has flourished. So this tells us a whole load about climate and CO2's effects on climate, but what it doesn't allow us to answer is what happens to our world when it has 425 ppm of CO2. You know, this is just not something that has happened in the last 800,000 years of our planet's history. But we can answer this by going deeper in time. And to do that, we need a different archive of our atmosphere. We run out of ice, but instead we can look to these beautiful tubes of mud. I realize that that's the kind of sentence that only a geologist says, but they are amazing. They come from the deep sea floor. And when we take them, wash out the clay and look at them under a microscope, the white color of this deep sea floor mud is made up of these gorgeous microfossils, each one about the size of a grain of sand, and each one an amazing record of the climate conditions in which it grew. These are single-celled organisms, they're called foraminifera, and when they grow, they take in the chemistry of seawater around them. And by measuring different chemical fingerprints within those shells, we can reconstruct climate through time. And this is very much what we do in my lab group at St Andrews. And if you're interested in how we do that, I can recommend our master's course in geochemistry to students young and more mature as well. Okay, so let's now fill in this figure. Again, we've got our human history piece on the right-hand side, and this is time in calendar years. Then in the middle, we've got time in thousands of years, so that takes us back 800,000 years with the use of the ice cores. And we're now going to fill in time going all the way back to 66 million years. So 66 million years is the demise of the dinosaurs. And this is our record of atmospheric CO2. Now, some people, when they look at this, will think, hey, you know, CO2 has been much higher before. So what's the big deal? Why do we need to worry about a level of 425 ppm? And to understand that, we need to dig in to the nuts and bolts of how CO2 actually traps heat and insulates our planet. So we're going to dig into some nitty-gritty physics, but we are going to do this through the medium of dance. So in order to help me with this, I would like a brave volunteer. You're not going to be asked to come up to the front. I'm looking, actually, if I can, possibly, for a brave volunteer at the back of the room. Can I get a brave volunteer at the back of the room? And again, you don't need to be all that brave. I won't make you do anything all that silly. Fantastic. Thank you very much. Can we have a little round of applause for our brave volunteer? Okay. Hello, brave volunteer. What's your name? Olwen, brilliant. Olwen, if you could please stand up for me. Olwen, everyone, is going to be our sun. And Olwen is going to power this demonstration in the way that the sun powers our climate system. So all of the energy that powers our climate system comes from the sun, and it bounces its way through the 150 million kilometers of the vacuum of space down to planet Earth in the form of bouncing waves of light. So Olwen, I'm hoping you're going to give me a bouncing wave of light. That is a brilliant bouncing wave of light. Yes, brilliant. Okay. So Olwen's bouncing wave of light has flown through space, and it collides with me. I'm planet Earth in this demonstration, and we're going to talk about the energy and the temperature of planet Earth. And in real kind of physical detail, energy and temperature is a measure of the bouncing around speed of atoms. And so when sunlight, can we have some more sunlight, please, Olwen? Perfect. And when that collides with planet Earth, the atoms of planet Earth bounce a bit faster. Now, anything that can take in some energy and have some bouncing atoms will give out some energy as well. It will re-radiate some of its energy. But because the Earth is cooler than the sun, instead of giving out energy as visible light, like the sun, right? We see the light from the sun, but we don't see light emanating from the Earth. The Earth gives out its energy as infrared radiation. And infrared also is a bouncing wave of light, but it's got a longer wavelength. So I'm going to send some infrared light back out into space. Okay. Now, if that was all there was to our planet's climate system, planet Earth would be a very chilly minus 19 degrees C. We'd be a frozen ball of ice in space. And 200 years ago, a famous mathematician called Joseph Fourier figured out that, well, this can't be it. There has to be something else. There has to be something that insulates that heat and stops it leaving planet Earth. And that substance, and this is where the rest of you, Owen is going to stay with us as sunshine at the back, but this is where I'm hoping that the rest of you might join in a very low-key way by being our most important molecule, carbon dioxide. So I don't know if you've ever been a carbon dioxide molecule before. It's very simple, though. We're going to have one carbon atom, which is your head, and two oxygen atoms, which are going to be your fists. And they're connected by these wonderful covalent bonds in your arms. And you're going to bounce like a carbon dioxide molecule, because carbon dioxide molecules, they vibrate in the atmosphere, and they have two vibrational modes. And so please, if you'd like to, please do join in. The first vibrational mode, okay, we've got our oxygen atoms, our carbon atom. The first vibrational mode is this. And that is wonderful. You are a brilliant room of carbon dioxide. And the second vibrational mode is this, okay, slightly trickier. And if you're feeling really ambitious, you can try and kind of put these both together. That's really difficult. Okay, a round of applause to all of you guys. Okay. Now, we are going to try and put all of these bits together. So, Owen, can I have another bouncing wave of infrared light? Pew! And that bounces straight through our atmosphere because CO2 doesn't like the very fast wavelength of visible incoming light. But then, when planet Earth receives that light and sends back its radiation as infrared, that bounce in the infrared is, and can I have your CO2 molecules again, please, has a similar wavelength to the bounce in the CO2. And so what happens is I try and fly back out to space, but instead I collide with the CO2 in the atmosphere because we're bouncing with the same kind of frequency. The CO2 in the atmosphere can then send infrared back down to planet Earth, making planet Earth bounce a little bit more. That infrared then tries to get back out to space again. Oh, but there's more CO2. Okay, so we bounce back down to Earth. And you can imagine that as we add more and more and more CO2, it gets harder and harder and harder for the infrared to escape back out to space, thus trapping heat around the surface of the planet and warming up our planetary temperature. It's analogous to a kind of a blanketing effect, to wearing lots of coats. It traps heat around the surface of our planet. Huge round of applause to all of you guys, and especially to Owen, our wonderful sunshine. So the science of this is nothing new. The way that CO2 traps heat, and in fact, a calculation into the impact of that on Earth's temperature was first performed way back in 1896 by Svante Arrhenius, Nobel Prize-winning chemist. He did this calculation, apparently to take his mind off a messy divorce. Slightly strange self-help mechanism, but we're not all Nobel Prize winners. And in this amazing paper, he gets to, if you're a geologist like me, Section 5, geological consequences, and you just love to see this. He says, I should certainly not have undertaken these tedious calculations if an extraordinary interest had not been connected with them. And he goes on to say, I speak to my geologically minded friends, and they tell me that there have been ice ages. And I bet that was because of lower CO2 in the atmosphere. And as we've now seen, tick. He said, we also can find the remains of tropical plants and animals at high latitudes. And so in the distant past, when they were alive, it must have been warmer. And I bet that that was more CO2. And as we've now seen, indeed, he was right about that too. The only thing he was wrong about was he said, we're adding a lot of CO2 to the atmosphere in this industrial revolution that we're going through, and that would have the potential to warm the planet in the future. However, it's a very inefficient, messy, and wasteful way to produce energy. So we'll have figured out something better before this becomes a problem. Unfortunately, that was his only mistake. Okay, so let's now return to our geological history of CO2 and provide some context for what these elevated levels have done to our planet in the past. And the most striking point we could take would be these peak CO2 levels of around 1,500 parts per million in a time called the Eocene. And this is a world which has Arctic alligators. It is a completely different looking planet to the one that we live on today. Completely different, I should say, all the continents are in roughly the same place, but it is a much, much warmer world, as we can see from this proliferation of tropical fauna and flora. How about our level of 425 parts per million? Well, we find that most recently 3 million years ago. It's a time called the mid-Pliocene, and it's not a time with Arctic alligators. It's a time that does have ice sheets in the polar regions, but those ice sheets are considerably smaller than they are today. So this figure is from the Intergovernmental Panel on Climate Change report, and it shows Greenland and Antarctica with their Pliocene ice sheets in this grey colour. Right, so today, both of these regions are covered in ice. In the Pliocene, these ice sheets are considerably smaller, giving a sea level that is globally around 10 meters higher. So what does our planet look like with 10 meters higher sea level? Now, the key takeaway from this is not that climate change comes with creepy music. I can't promise that in the future. It is, of course, that this is a level of disruption to the world that we know and love that would be very, very hard to deal with, to adapt to. So we have a window of time to prevent sea level from getting back to these geological levels. And you might be wondering, well, why aren't we there already? If this was the amount of sea level rise, this is how much higher sea level was last time CO2 was as high as it is today, why haven't we seen this level of sea level rise? And it's a good question, and I want to illustrate the answer to it with an experiment. So we're all going to be both scientists and theatregoers here. I want you to suspend initially your sense of disbelief as I tell you that this is planet Earth, okay? So this is an entirely dry planet Earth, and we're going to see what happens to planet Earth when we add some heat. Okay, and you are here, we're at a science festival, so we're going to be scientists as well, and I want you all to hypothesize what might happen to planet Earth, this dry planet Earth, as we add some heat, okay? We're all prepped. If you need to prep in any particular way, feel free to do that. Okay, so here's our dry planet Earth. We're going to add some heat, and okay. Whose hypothesis was proved correct? Judging by the number of people who cover their ears, most of you, that's great. Okay. We're now going to add some heat to a second version of our planet. But this blue planet Earth is going to have an ocean, okay? This ocean might be confused with the water that I'm pouring out of my water bottle, but this is going to be today's ocean. And just a normal balloon, and just some normal water. Okay. So we're going to repeat that same experiment. We're going to add some heat and see what happens to this watery planet. And of course, our real planet is watery. This is a view of the Earth from space, rotated to look at the Pacific. Our planet is 2/3 oceans. Okay. Hypotheses formed? That has never happened before. That has never, ever happened before. Let's repeat it. Okay. I don't know, these are, yikes. Take two. More reassuring sound from that balloon. Okay. Version of watery planet number 2. So, what you can see is that with this balloon, the flame has touched the substandard balloon pack. I'm sorry. The Anstruther Corner Shop has not delivered. But you got the message. You could see that on that second balloon, and here, this one I prepared earlier, that second balloon, we had the flame licking the skin of the balloon for considerable time before it popped. So what's going on here? Well, heat, again, is that bouncing around energy of atoms, that bouncing around speed. As we added heat to the skin of the balloon, the atoms bounced so quickly that they ripped apart. When in the second case we performed the same thing, we added the same amount of heat, we didn't get the skin of the balloon to bounce as quickly, it didn't heat up as much, because instead a bunch of that heat was transferred into the water, and water soaks up an awful lot of heat. It's heavy, and it has something called a high heat capacity. Now, our planet is 2/3 oceans, and those oceans are, in the case of the Pacific, 5 kilometers deep. And you won't feel, and indeed that water at the bottom of the Pacific has been at the bottom of the Pacific for over 1,000 years. So the whole planet doesn't warm up until all of that water warms up. And that does take some time. It takes on the order of several thousands of years, giving us a window between now and some time in the future to try and reverse this CO2 change before we catch up to that Pliocene 10 meters of sea level rise. So that's in the distant future, but let's now look at what's happened in the more recent past. I'm showing you here temperature change over the globe relative to part of the latter 20th century, with years counting through on the top. And you can see that compared to pre-industrial, we've now experienced about 1.2 to 1.3 degrees C of global warming. Now, 1.2 degrees C sometimes doesn't sound like all that much. We're used to feeling much bigger changes in temperature day to day, but bear in mind that most of those temperature changes day to day are just the movement of parcels of air around our planet. That's very different to warming up of our planet as a whole. And I think a useful analogy for that is that if you picture the peak of the last ice age, that time with a kilometre of ice on top of where we're currently sitting, a time that we'd all agree and kind of feel is much colder than today, that's actually only 4 degrees colder at a global scale. So an ice age unit of climate change is 4 degrees. So 1.2, 1.3 degrees is already about 30% of an ice age-sized change in climate. It's a lot of extra heat trapped near our planet's surface. And that extra heat energy causes a nuisance, right? It powers different aspects of our climate system, and it creates impacts worldwide. And the impacts, on the one sense, are planetary, but actually, the real impacts are on human lives, right? We're not. I'm concerned about the planet, but ultimately, I'm more concerned about people. People whose homes are built on permafrost that's melting, people whose crops are failing, who are feeling the effects of ever more devastating tropical storms. Tropical storms are fed by warm ocean water, so as you warm up that water, it gives more energy to make those storms more destructive. And people who are feeling changes in fires and flooding. And I will say these impacts are being felt worldwide, and they are already being felt. This is not something that's about polar bears 200 years in the future. This is about people, and it's about people here and now. I'm going to talk about 2 of these impacts in particular because I think they are really important. They're the ones that are to do with changes to the water cycle. Now, we've known since the Industrial Revolution that for every 1 degree C that you warm up a parcel of air, it will hold 7% more water. And so if we have warmed up our atmosphere by 1.2 degrees C, that's about 10% more moisture that the atmosphere can now hold. And this has 2 really important implications. The first is that in places that are hot and dry and where water tends to evaporate, the atmosphere is now thirstier, and so it will suck up more moisture. And that makes these hot, dry places hotter and drier, and thus more prone to larger forest fires. On the other hand, we have places where water tends to cool in the atmosphere and condense into raindrops, and there are no prizes for guessing which of these categories Scotland falls into. In these places, there's now an atmosphere that is charged with 10% more moisture than it had pre-industrially. And that means that any heavy rain event can now be 10% wetter than it was pre-industrially. And this is something, a really kind of small-scale local example, but one felt at St Andrews University, which has been around for 600 years. It's had a bunch of old buildings with gutters that have been fine for most of its history, but within the last few years, these gutters are now proving too narrow to deal with the amount of rainfall that we get in heavy rainstorms, and so we've had to replace these with wider gutters because there was so much loft damage from rainwater piling up. More dramatically, this is an image of the A816 in Argyll. This is from last October in the aftermath of Storm Agnes, where a whole month worth of Argyll's rain fell in 36 hours. And if you're familiar with the climate of Argyll, you'll know that that's an awful lot of rainwater. The result of this was it destabilized this hillside. It sent down 6,000 tons of debris, and it led to this road. I mean, this road in this position is still blocked. It's still, you cannot drive this. There is an alternative, but that took several months to enact. And so the children who live in the village at the end of this road had to go to school by boat, which I'm sure for about the first 2 days was quite good fun, but as December drew in was considerably less jolly. Okay, so climate impacts are serious and they are human impacts. And we can't talk about these impacts also without mentioning that they are acutely unjust. And that's for two main reasons. There's an international climate injustice where there's this huge disparity in the severity of climate impacts. So many of the countries that will feel the effects of climate change most strongly are poorer countries. They're in the subtropics, or they're low-lying. And so their impacts will be greater. And these countries have also done the least to cause the problem in terms of cumulative carbon emissions. So this shows the total amount of carbon emissions per person since 1850 for a set of countries. You can see the UK here is still, we're fifth in the world. Woohoo. We have this huge historical legacy of our early industrial revolution. We have put a lot of carbon into the atmosphere. And while China today is the world's largest overall emitter, you can see that per person, the carbon emissions for China are substantially smaller than for these richer countries that developed earlier. So this is the international aspect of climate injustice. And then the other one, which I think about a lot as a parent, is the intergenerational one. This is my son, John, who is now 6 years old, right? For him, 2100, this isn't some statistic. This isn't just some figure in a report. 2100 is going to be a lived reality. And what kind of world he grows up in, what kind of world we leave him, fundamentally depends on what pathway we take in terms of carbon emissions. To look at that in a bit more detail, this graph shows the total amount of CO2 that we add to the atmosphere, and then the total amount of global warming that results. There are a bunch of different pathways that can lead to different amounts of carbon appearing in the atmosphere at different times, but ultimately all of these different pathways shown in these different colors, they collapse onto the same line. The take-home message is just the more carbon you put in, the more warming you get, and the more warming you get gives more energy to cause havoc with the hydrological cycle, to melt ice sheets, and generally to leave a less safe planet for our kids. So how do we stop this? Well, the good news is that continued global warming is not inevitable. We can stop our planet from warming, and to do that, we have to get carbon emissions to net zero. Now, net zero is a term that is increasingly commonly heard within the media, and I want to take a wee bit of time to explain this. And to do that, I'm going to collapse all of the beauty and complexity of our atmosphere into this rather rubbishy clip art bucket. Okay? So, our atmosphere is this bucket, and our carbon emissions are the water coming out of this tap. There is a small hole in the bottom of the bucket. Some of the CO2 that goes into the atmosphere gets taken up by the ocean or by plants, right? So there are ways that CO2 can come out of the atmosphere. But at present, this is a drip, and this is on full blast. And the consequence is that the level of water in the bucket, the level of CO2 in the atmosphere, is rising rapidly. Now, if you came into a room and you saw this bucket filling up with water and that tap, and you didn't want water to spill all over the floor, the thing you would, of course, do is turn the tap off. That would be the simple solution. And this is a zero emissions scenario. We've turned the tap all the way off, and the water levels now start to drain out. The carbon dioxide levels start to fall. But you might find that it's hard to turn the tap all of the way. The last bit might be stiff, or there might be some leak in the tap. And if that's the case, this problem is much harder in terms of how to stop the bucket from overflowing. What we have to now do is run around and see if we can find a hammer and a nail and tap a couple of extra holes into the bottom of the bucket. So these represent kind of carbon removal scenarios or offsetting scenarios. But just like in our analogy with the bucket and the hammer and the nail, they're hard to do, right? You need to find those hammers and nails, and you need to work out how to tap that hole. But you can, if done right, get to this same net zero emission scenario with a small drop still coming in and an extra drop coming out. So we need to get to net zero, and in order to do that, we need to work out where emissions are coming from and how to eliminate them. This, globally, is the breakdown of sources of greenhouse gases. A quarter of our greenhouse gases come from the production of electricity, and that is predominantly, that has historically predominantly been from coal and now to a lesser extent gas. About another quarter of greenhouse gas emissions come from deforestation and agriculture. Right? So the rest of this is kind of a fossil fuels picture, but there's also this important quarter. This is about land use. And this can be at times surprising, but bear in mind that half of the world's habitable land is farmed. That is a huge thing that we have done to the surface of our planet. And incidentally, 3/4 of that farmed land is used for livestock. We'll return to think more about that in a minute. About 20% of global carbon emissions come from heavy industry, so cement and steel production. About 14% from transportation, though note that in rich countries this is higher, so in Scotland this is 22%. Globally, 6% come from the heating and cooling of buildings, though again in Scotland this is higher. This is 28% of Scottish emissions from the heating of our buildings. And then finally, 10% of carbon emissions come just from the process of fossil fuel mining and extraction. Methane leaks out of coal mines. Flaring happens on oil and gas reservoirs. And there's a lot of energy used in just the process of fossil fuel extraction as well. So to get to net zero, we need to eliminate these sources of greenhouse gas emissions. And to do that, at least for 3/4 of them, the way we get there is by producing clean electricity and then by making everything that currently burns a fuel run on clean electrons instead. So how to fix climate change? The mantra is clean electricity and electrify everything. And we do also need to think about that land use part, less deforestation and less livestock. So let's have a quick look at what this looks like. Clean electricity is, as we'll look at more in a couple of slides' time, this is a problem that we have worked out how to solve. We will build out wind power, solar power, other clean sources, so nuclear, advanced geothermal. We know how to make clean electricity, so good news there. We then need to put those clean electrons into heat pumps in homes, into electric vehicles for transportation, and find low carbon and electric alternatives within industry as well. So let's look at some of these major sectors turn by turn. And we're going to start with clean electricity because this is the linchpin of that whole clean energy transition. This is some output from one of my favorite websites, earth.nullschool. It shows live wind speeds around the world. And this was on a wonderful day this summer, where you can see that the wind is blowing nice and strong. And this is really, it is honestly a blessing of the Scottish climate. Just how windy it is, both onshore and in particular off our coasts in our shallow seas. And so we have increasingly been able to capture that wind energy. And the amount of wind energy, this is now a breakdown of the energy sources on the national grid for the whole of the UK. Renewables are shown in this inner green ring, broken down by solar energy and wind energy. In blue, we have nuclear power and biomass. So these are two different but still low carbon sources of energy. And then finally, in red, we have fossil fuels broken down into gas and coal in the outside, and there's no coal being burnt on this particular day. So this was a good day, but now let's look at something that's just representative of the last year. So here is the last year. You can see that there has been, a bit more fossil fuel burning than on this particular day, but actually, less than a third. So 72% of the UK's electricity came from low carbon sources within the last year. And that's a complete transformation in how we get our electricity, and it has happened like that. So this shows the same figure, but just 6 years ago. And you can see that 6 years ago, only 48% of our electricity came from low carbon sources. And when I was born, which wasn't all that long ago, 2/3 of our electricity came from coal. This year, we will shut the final coal power station in the UK. So this has been a transformation in how we get our electricity, and it's been enabled by the remarkable fall in the cost of wind and solar. So I'm showing here the price in dollars per megawatt hour to make energy. This red line shows the price of electricity from solar. It's dropped by 90% in 10 years. And then this here shows the price of onshore wind. These are now the cheapest ways to get new electricity. And as of yesterday, excitingly, we are going to build yet another kind of 10% more capacity onto the grid in the UK in terms of these clean electricity sources. And the reason these have been able to get so much cheaper is simply we've done more of them, and as we do more of them, we get better at doing them, and so they get cheaper. So this shows that what's called a learning curve, the cumulative amount of solar that has been installed, and the way that the price of that solar has come down. And these are both logarithmic scales. As you build more, you get better at doing it, and so it gets cheaper. And so you can then build more of it, and so it gets even cheaper. It's a virtuous cycle. And as a result, we are, as a planet, installing an incredible amount of solar electricity. This shows cumulative solar capacity for the world. This shows it for China alone. You can see this, it's about 40% of the world's solar. And the United States and India, there is enormous growth in solar capacity. There's rapid growth in wind as well. And so if we look at the proportion of electricity worldwide made up by wind and solar, you can see that that's grown. In 2000, this was way less than 1% of global electricity. About 10 years ago, it got to about 2%. This year, it will get up to 14%, and it's growing exponentially. And we can take a number of examples and look at how this is indeed replacing dirtier sources of carbon on the grid. So this is US coal versus renewable energy consumption. And intriguingly, this is the presidency, the previous presidency of Donald Trump, elected on a mandate to bring back coal. But the economics of this, even with favorable politics, just didn't make sense. Coal use has continued to decline and has been overtaken by renewables. So we're making huge headway on clean electricity. The next thing we need to do is clean up those other sectors, power them with clean electrons. And to think about transportation, we're going to start with a game of Spot the Difference. In the left-hand picture, these are both of Fifth Avenue in New York. The first is in 1900, and here this is a game of Spot the Car. And if you look really carefully, you might just be able to see that the first motor car on the street is here. All of these other vehicles are horse-drawn carriages. Now, there was, I'm sure, kind of a charm and romance to horse-drawn carriages, but they also came with their own emissions, which were pretty messy. And as a result of all of that mess and all that expense of keeping horses, at the point that cars had started to reach about 5% penetration into this market, the rest happened extremely quickly. So fast forward 13 years, and now all of these vehicles, except this one right here, are internal combustion engine cars, and there's just one horse-drawn carriage. And this timescale of about 13 years to transition a new technology is typical of many of our technologies, from microwaves to cars to telephones, and it is looking like it's true for electric vehicles as well. The world leader on this has been Norway. In 13 years, they went from 0% up to 80%. Updated this year, they'll be up at 95. This goes to 2022. It's very easy to say, oh, well, but Norway, it's a small, rich country. What about a larger market? The largest market by far worldwide for cars is China. China has a car market that is bigger than the US and all of Europe combined. And you can see here that China in 2020 was about 5% of new cars were electric vehicles. By 2022, it was 20%. Last year, it was 35%. This year, some projections say it will be 50%. That is an enormous transition and an enormous growth, and is something that actually tracks the planet globally onto something needed to stay at net zero by 2050. And there are other good news stories in here too, namely that we don't need to replace all of the energy that we use today in this clean electricity world. We only need about half of it. Why is that? It's because these electric solutions are so much more efficient than the fuel-burning incumbents that they're replacing that you can do the same thing with much less energy. And a great example of that is cars. If we look at an internal combustion engine, of the chemical energy in the petrol that goes into the tank, only about 30% makes you go forward. The rest, 70%, is lost as heat and noise. In contrast with an electric vehicle, of that energy charged up in your battery, only 20% is lost, and the 80% remainder makes you go forward. And this is true dramatically in terms of electricity production as well, and in terms of heating of homes. So there is a huge efficiency win in this transition away from fossil fuels. And finally, not a climate benefit, but an enormous health benefit as well. Air pollution is the #1 cause of premature death worldwide. Somewhere between 4 and 9 million people are lost every year from air pollution. And this is predominantly the result of fossil fuel combustion. Okay, now I want to leave time for questions, so I'll just quickly mention that if all of the world's cattle formed a nation, the United States of cows, they would be the 3rd largest emitter of greenhouse gases. So in terms of how we address that kind of agriculture and land use piece, shifting away from meat-heavy diets is going to be part of that picture. Are we making any progress? And the answer is yes. These are annual CO2 emissions for the UK. And you can see that emissions have been falling rapidly and are now at levels that were last seen in the 1880s. So progress is being made nationally and also globally. This is what the world would have looked like without any climate policies. And we have avoided this world. And this is a catastrophic world, right, with over 4 degrees C of warming. Our current policies put us on about 2.5 to 3 degrees C. Our pledges and targets get us lower. And that's great news, because every fraction of a degree warming that you avoids climate impacts and leaves a safer world, ultimately, for our children. So progress has been made, but as we've seen so far, a world with 1.2 degrees C of warming is already a more dangerous planet, and 1.3 is more dangerous than 1.2, etc., etc. So to ensure a safer, more livable planet, we need to keep trying to bend this curve downwards. How can we do that? Well, as individuals, there are, of course, things you can do in your home, and this is a big one in Scotland: insulation, draft proofing. If you can, investigate a heat pump. In terms of diet, I'm not going to kind of preach that everyone should kind of overnight become vegan. That's a difficult lifestyle choice. But you can get a lot of the way there in terms of your dietary emissions just by eating less meat and more plants. And in terms of transportation, this year in the UK, the median electric vehicle will cost the same as the median internal combustion engine. I have one. They are also tremendous fun to drive. So all of these individual actions do add up, but they do one other really important and, I think, underappreciated thing, which is that they send signals to markets which can then act at a much larger scale. By policy support for some of these new technologies, by showing to companies building things like heat pumps or electric vehicles that there is demand for them, by spurring on further research and development to keep making these solutions better and better. And we get there both with our individual actions of taking these different actions here, but then also critically by talking about them, by pestering, by in particular pestering our politicians. And so if you do one thing as a result of coming to this talk tonight, please just talk about it. Tell somebody that you know, and those are the people who you will influence most strongly. Tell somebody that you know that if you leave CO2 this high, you get to a sea level rise of 10 meters, last seen 3 million years ago, but also that 72% of our electricity now comes from low carbon sources, so that we are making headway in solving this problem. Okay, so to summarize, I've talked about the 3 S's of climate change: simple, serious, and solvable. We have known for well over 100 years that CO2 is the key control on our climate. It has changed climate in the past, it is changing it today, and will control it into the future. We've looked at the serious impacts of a changing climate. These are not so much something we need to do to solve or kind of save the planet. We need to do them for each other, and in particular for the generations that will come after us. And we know how to solve this problem. It's clean electricity and electrifying everything. Those solutions are growing incredibly rapidly, but much more action and progress is still needed. Okay, that's it. Thank you very much. And I'll be very happy to take any questions from the audience. We've got people watching online as well. Just like in one of my lecture classes, there are no such things as stupid questions. If you have a question, probably the rest of the room are thinking the same thing. So please ask away. Yes, in the middle of the room here. And there's a microphone coming in, so you don't have to shout out.
Thank you. Do you have any views on degrowth as a strategy?
It's a really interesting question. So degrowth, for those who aren't familiar, is the idea that a major driver of emissions is the economy, the amount of stuff we produce, and so one control, an important control on emissions, is the size of an economy. There's a good correlation between economy size and emissions. The really tricky thing, and so some people have strongly proposed that you should degrow our economies in order to try and limit emissions. And it's a view that I'm interested in and have some sympathies towards. The reason I don't place too much emphasis on it is I think it's really, really hard to enact. I want solutions that we can do today and tomorrow, and convincing people, the economy and growing the economy is still voters' number one concern, right? If you look at the election polls in the US ahead of this presidential election, the economy is the number one concern of voters. So flipping the growth of the economy from being voters' number one concern to all of our democratic societies deciding collectively to degrow is really, really hard. It may be possible, but I don't know how we can do it as quickly as we need, right? Because we need to act really fast. And so I think we need to really spend as much of our energy as we can on supporting the solutions that we have right in front of us. Yes, another question down here. There's a microphone.
Besides CO2, what are the other potential gases like used in refrigeration and all, which are also very dangerous?
Great question. So CO2 is the major greenhouse gas. After CO2, though, methane is the next most important greenhouse gas. And then after methane, it's a number of others, so some of the nitrous oxides. And then after nitrous oxides, it's things like some of the CFC-type compounds that are used in refrigerants, like you say. All of these are important. We don't get, I've talked about net zero and net zero in terms of greenhouse gases as a whole. And we often, because CO2 is the big one, we often do kind of convert that into CO2 equivalents. The reason that I think it's keeping the focus as much as we can on CO2 is because CO2 is the one that once it goes into the atmosphere, it stays there almost irreversibly. It stays for thousands of years. It takes thousands of years to get soaked up by, if you did nothing else, you'd have this, it is getting taken up by trees in the oceans, but that sink is quite slow. So CO2 molecules that we put into the atmosphere today are likely to be in the atmosphere for thousands of years. In contrast, methane has a lifetime of 10 or 20 years in the atmosphere. And this is really useful, actually, because if, for instance, we wanted to prevent about 0.2 degrees C of extra warming, if we managed to eliminate methane, that would almost instantly happen. We would feel that very quickly because the methane would come out of the atmosphere and it is currently responsible for a few tenths of a degree of warming. And then similarly, in those other gases, those refrigerants, many of them do have alternatives that don't have as high of a global warming potential. And there are kind of international efforts underway to try and encourage the industry to move towards those lower greenhouse gas potential alternatives. But the focus on CO2 is just because once it gets in, it stays in for an awfully long time. Great question, though. Thank you. Yes, up at the back of the room.
I've got some for the online audience, if I can pose those. So got one from Jeffrey, who brings in a bit of a big question, says, what about politics? We have increasingly detached nation states. How will coordinated action be possible to make this happen, or is that going to be too late?
It's a great question, and it's one that is hard to answer for a simple-minded physical scientist. I will say that in part because I think this is, I think politics is genuinely difficult, right? The UN meetings on climate change have been genuinely, they have struggled to make really big progress. They struggled for many years to get some kind of silver bullet solution. Can we kind of globally put a price on carbon or something like that? That is a really, really hard thing to do. And so, in fact, the greatest progress we've seen in those meetings is the Paris Protocol that says, actually, we're not going to try and have a one-size-fits-all solution, but we are going to ask everyone what they can do and then encourage them to do that and then do more and more, right? And so some degree of granularity is actually perhaps not a bad thing because it allows countries flexibility to do things that they are able to do. But I realise that's maybe a little bit of a kind of wishy-washy answer, so let me give a slightly more kind of concrete answer why, although I do worry about this, I do also take some hope from the fact that, for instance, the state with the highest installed capacity of renewable electricity is Texas. Now, Texas is not a state that leans towards ambitious climate policy, but if you tell people that they have the option of having a more secure energy supply that's going to cost them less because it's the cheapest way to get electricity, you don't really need to, you just vote for that with your wallet, and that transcends politics. So I take heart from the fact that the clean alternatives to fossil fuels have become so much cheaper that in part it gets around the political question, because regardless of your politics, you will typically do the cheapest thing. That's the kind of most optimistic view I can take, but we do still need, to this final point, we do still need further progress and more action, and governments have an important role to play within that. And this is where it actually does really need the voters to be concerned about it, to talk to each other about it, and to be encouraging of solutions. Politicians hear a lot from NIMBYs saying, I don't want this in my backyard. Have them hear from some YIMBYs as well, some yes, I'm fine with this in my backyard, because I recognize that, for instance, having more power transmission, more pylons, is going to be part of what gives us a safer planet for our kids. Yes, maybe at the side here. Oh, yeah.
A geological question. The land is warming up, and what can be done about that?
So, I guess if I understand you correctly, the primary reason for the land warming up is having too much carbon dioxide in the atmosphere. If you stop putting carbon dioxide into the atmosphere, the land will stop warming up almost instantly. And this is due to an interesting balance between the fact that if you stop putting carbon into the atmosphere, it will still keep coming out of the atmosphere, right? So emissions go down. So you might say, oh, wait, should it not get cooler? Unfortunately, that's offset by the fact that the ocean is still warming up. And it ends up being that when you get to net zero, those two things balance each other. So you experience a bit more warming due to the ocean continuing to warm, but you start to get an opposing effect in terms of carbon coming out of the atmosphere. And so when you get to net zero, the land stops warming up. When you can more actively remove CO2, then you start cooling the planet. And this actually is an interesting geological point. We have had intervals in the geological past where CO2 has risen rapidly in the atmosphere. The most recent one of these was 55 million years ago. It's an interval called the Paleocene-Eocene thermal maximum, or the PETM. In the figure that I showed, it's going to look like a spike. And the spikiness of this on this timescale is in some ways good news. It gets to the point I'm wanting to make, which is that carbon went into the atmosphere very rapidly, but then it also came back out of the atmosphere. Now, the speed at which it came back out of the atmosphere looks quite quick. It looks almost instantaneous on this graph. Unfortunately, it took 400,000 years, so kind of geologically quick, but not quick for humans. It came out of the atmosphere because primarily rainwater, the planet got warmer, rainwater got more acidic, and that made the chemical reactions between CO2 and rocks at Earth's surface go faster, and that sucks CO2 out of the atmosphere. So that takes hundreds of thousands of years left to its own devices. A bunch of geologists are now working on whether we can speed up reactions like that to make them go faster. This is called enhanced weathering, to see if we can more actively remove CO2 in the ways that CO2 was removed back in geological history as well.
You explained how the presence of greenhouse gases in the atmosphere causes a rise in seawater levels. And then you also demonstrated through the balloon experiment that the presence of water helps the surface of the Earth to endure more heat.
Yeah.
Why is it not the case then that as the seawater levels rise, it actually helps the Earth be better at resisting global warming?
It's a good question. The quick answer is it's the same. Absent the ice melt, there's two bits to sea level rise. The first is actually just that warmer water takes up more space, but it's still the same amount of water, right? So it's sucking up heat and it's just expanding, but you haven't put kind of extra water in that case. In the case of ice melt, you have put more water in, and that did suck out heat energy. When you converted that ice into water, that sucks out a lot of heat energy. It's the equivalent to putting an ice cube on your hand. You can feel heat getting sucked out from your hand. So that does soak up heat energy, but not enough to offset the amount of global warming that we've seen. One more question. Great.
We've heard a lot in the past about the possibility of carbon capturing. Just how physically viable is it to pump billions of tons of gaseous carbon content back in the ground under high pressure into liquid state and conveniently using the depleted oil wells?
Really good question. And there's different bits to the answer. So actually on the kind of most direct example that you talked about at the end there, right? The idea that could you squeeze CO2 into depleted oil reservoirs and keep it down there? We actually, it sounds really far-fetched, right? But we actually know that we can do this because this is actually a method that the oil industry used for several decades. And it used to have a different name to carbon capture and storage. It used to be called enhanced oil recovery, or EOR. It turns out that if you squeeze a depleted oil reservoir full of CO2, it can squeeze out more oil. And there was a brief period of time where the industry said, and look, this is wonderful because we'll even be able to sell the oil and then this will all kind of pay for itself. Not mentioning the fact that there's a lot more carbon per unit volume in oil than in CO2, so that would be a net source of CO2 into the atmosphere. Now, these days when carbon capture and storage is discussed, it is no longer being touted as enhanced oil recovery alongside. And it is something, and we do know how to do it, right? So the engineering solutions to that are there. The trickiest bit is where do you get the CO2 from? And the easiest place to get CO2 from are concentrated regions of CO2. So the stacks out of cement works or out of gas-fired power stations. They might have more than half of that gas might be CO2, making it easy to catch quite a lot of CO2 within that chimney. And I will say that all of the scenarios that get us to, that get us to 1.5 or even 2 degrees of warming have considerable amounts of carbon capture and sequestration within them. It's difficult. It costs money. And some people are kind of nervous about it because it's inherently a solution that is very tied in with the oil industry. But cement works, in particular, are really hard to decarbonize. And until we've worked out ways to make cement without producing carbon, CCS is, carbon capture and storage, CCS, is a good alternative. Or at least it's a necessary alternative. It's better than having that CO2 go into the atmosphere. Similarly, Our energy, our electricity system will be it's already dominated by wind. It will be increasingly dominated by wind and solar. What happens if we have a Dunkelflaut, a wonderful German word meaning a wind drought? This can happen for a couple of weeks at a time. It's rare in a place as windy as the UK, but it can happen. The best near-term solution that we kind of have on hand at the moment is we could burn gas and capture the carbon. So I think that we will need to do that, and we know how to do that, those bits, out of a concentrated source and into an ore reservoir. I think we also need to remove even more carbon directly out of the atmosphere itself. So this is called direct air capture, or DAC, and that's much harder, because now we're dealing with something that was 400 parts per million, which as a number seemed like quite a lot when we were talking about 2,000 adults peeing into an Olympic swimming pool, but it is still relatively diffuse and dilute, and it's difficult. It's possible, but difficult to capture that carbon. There are ways that you can do it with big fans and particular chemicals that absorb that CO2. Trees are very good at doing this as well, and so can you capture carbon in trees and then make sure that that carbon is stored and doesn't go back into the atmosphere. We will need to do this as well if we want to avoid long-term these kinds of catastrophic sea level scenarios. But doing that is difficult, and that is still a major engineering and technical challenge. And so when I say that we're making progress, we're making a bunch of progress. And we need to keep we should celebrate that, right? We've transformed our electricity system, our energy system. And most of us haven't really noticed in the UK that that's happened. And in many ways, that's a success. But there are going to be harder things that still need more research, development, more investment, government support. So we are not there yet. There's still a lot to do. And I think on that note, I'll wrap up. Thank you very much.